Sir, Professor Lambotharan serves as the Director of Institute for Digital Technologies at Loughborough University, London, where he is also a Professor of Signal Processing and Communications. He earned his PhD in Signal Processing from Imperial College, London in 1997. During his career, he has held positions such as a visiting scientist at Cornell University and a postdoctoral research associate at Imperial College, London. His industrial experience includes valuable contributions to the Motorola Applied Research Group in the UK. From 2002 to 2017, Professor Lambotharan made significant academic contributions as a lecturer at King's College London and as a senior lecturer at Cardiff University. His current research interests are at forefront of technological advancement covering 5G networks, MYMO, signal processing, machine learning, and network security. With over 270 journal articles and conference papers, Professor Lambotharan's work has been widely recognized, gathering over 6,500 citations and achieving an H index of 43. He is a fellow of IIT and a senior member of IEEE, and he holds editorial position as a senior area editor for IEEE transactions on signal processing and as an associate editor for IEEE transactions on communications. Please join me in giving a warm welcome to Professor Sangarapillai Lambotharan.
Ladies and gentlemen, thank you for the opportunity to present my work. This work is mainly for wireless communications and resource allocations problem. So I understand most of you are from computer science background. My background is from engineering, but I work on telecommunications, wireless communications, including radar sensors. So I will make my presentation, I will explain some key concepts. My intention is to go through these game theory optimization and machine learning algorithms for wireless communications and radar. So I'll go through some examples before I look into how I use that to solve telecommunications problems. So my background, as you have heard, is algorithmic signal processing. So I have been working in developing signal processing algorithms. Okay. Right. So before I start, just to understand the audience, can I ask how many of you heard or worked on game theory? Game theory, two of you guys, and convex optimizations. And I think all of you will raise your hand for machine learning. So my intention is to go through some simple examples from game theory, which is introduction to the game theory, some classical examples. Then I will go through how I apply that in wireless communications. As you will see, game theory, optimization, and machine learning are kind of related. I'm using all of these to optimize some transmission parameters in wireless networks. So before I go into my talk, let me introduce you. Loughborough University. Loughborough University is located about 100 miles north from London. The location is, we also have a campus in London, so I come from the London campus. In terms of the campus size, Loughborough University is located around 600 acres of land, so it's the biggest campus in the UK in terms of land size. And Loughborough University is well known for sports-related studies. We rank, QS ranks #1 in the world. So probably if you watch Olympics, you will see some of the UK players are from Loughborough University. And we are also well known for our degrees in engineering, STEM-related subjects. So these are, when students apply for university admissions, they look at the UK ranking of the university. So we normally come into one of the top 10 in most of the rankings. And also we are well known for employability. So we have most of our degrees very much related to industrial projects, etc. So students spend some time in industries, etc. So because of our reputation in sports, after Olympic in England, UK, we opened a new campus in London. So that is only for the postgraduate studies. So we have several institutes within our London campus, and I belong to Institute for Digital Technologies. So these are the members of the Institute for Digital Technologies. It's an interdisciplinary team. So we have engineers, computer scientists, and we have this professor of economics. So he looks into the artificial intelligence, machine learning, etc. on the economy and how that affects the economy, etc. So we have people from PhD, finance, etc. So we also look into digital finance, blockchain technology, and that sort of things also in my institute. So in my talk today, I will be focusing on wireless communications. Right, so what is game? So we play all these games. So when we play games, we have strategies. So if you play chess, when you make a move, before you make your move, you need to understand what your opponent will do when you make a move. And you should know your opponent will also think about what you will do for the move that you're going to make now. So before you make any move, you will look into the strategy, what your opponent will have, right? So this is a football game, for example. If the player is right-footed, he will tend to kick the ball towards the left. So the goalkeeper will lean, knowing that the players will kick the ball towards the left, goalkeeper will lean towards the left. And you should know that the goalkeeper is going to lean towards the left. So it is sometimes beneficial for not to kick the ball to the left, but sometimes to the right. So you need to just randomize your strategy so that your opponent will not be able to predict what you're going to do. So this is covered by mixed strategy games. So I'm going to go through one of three classical examples for game theory, and then I will tell you why I'm interested as an engineer who designed wireless communication systems. So before I introduce game theory, I don't know if you have seen this movie. It came in the 90s. This movie is about Nobel laureate John Nash. Yeah. So in the movie, he is John Nash. So John Nash, I will talk about him later. He made significant contributions to game theory. Unfortunately, he died a few years back in a car accident. So he is no longer alive. So he is John Nash, who won the Nobel Prize for economy. So what he has done is he came up with mathematical models for strategic interactions, right? So whether it's cooperative or non-cooperative, you will have some strategic interactions, and then what Nash has done is, using some mathematical analysis, you can predict the outcome of any strategic interactions. So some strategic interactions are very complicated. You need to use a mathematical model to predict what will be happening in that strategic interactions, what will be the outcome of the strategic interactions. So that's why he won the Nobel Prize for economics, because the prize is for economics.
Nash equilibrium was the
Correct. So the outcome of the strategic interaction is known as Nash equilibrium. Okay. So I will be talking about that in a minute. Why he won that in economics is because that mathematics is used mostly in economics for market competitions and understand how firms behave and etc. So I have been applying game theory for different problems in engineering, mostly for resource allocations, for wireless communications, wireless, smart grids, and also collaborative data mining. So today in my talk I will be only focusing on the first three. Right, to give you an introduction to game theory, if you want to study game theory, you take any textbooks, you will see this example. Okay, this is a textbook example. What happens here is, I'll explain that to understand what is Nash equilibrium. The police has two members of a criminal gang, like A and B. So two members of the criminal gang. Police do not have enough evidence to convict the gang members for the primary charge. So what police has some evidence to charge them for 6 months in prison. So what the police have done is they put the person A and B in a separate cell, and the police make an offer. So this is A and B. If A and B, if they can testify their crime, if they can tell, if A can tell to the police what B has done, then A can go free and B will get 20 years in prison. But if A and B, they cooperate between them, so the police wouldn't have enough evidence, so they will be charged for 6 months in prison. So here A and B, so A and B defect means they are telling, they are giving the evidence to the police. So the police have enough evidence to put them both 8 years in prison and 8 years in prison. And if A becomes silent, and if A doesn't give any evidence to the police, but if if B is silent, B is cooperating with A, so B doesn't give any evidence to the police, but A is cooperating with the police or defecting his friend, then A will get 20 free and B will go 20 years in prison. You understand the game? So A and B are put in a separate prison. If you are not able to see this one, this is better. Okay. So to summarize, so if A and B, they are cooperating between them, so they are not telling anything to the police. This is A will get 6 months in prison and B will get 6 months in prison. If they are both telling to the police the crime, so they are defecting each other, then they get 8 years and 8 years. And if A is cooperating with the B and B is B is not cooperating with A, but A is cooperating. Say it again. So here B is telling, not telling anything to the police, so he will get 20 years in prison. But A is telling everything to the police, so A will go free. So this is what will happen. This is what the game is. Okay, police put them in separate prison. So now by looking at this, we can tell what A and B is going to do eventually. Okay, so how we do that is, so suppose if A decided to defect B, so A is going to tell everything to the police. Now we have a choice, 2 choices. B can defect A, so B also sending everything to the police, so B will get 8 years for that. Or B can cooperate with A, not telling anything to the police, then B will get 20 years. Because that was the deal given by the police. So A is going to get free. So suppose if A chooses to defect B, B will think, I am better off doing that than that. So if A decided to defect B, B, regardless of knowing what A is going to do for this particular situation, B is better off to defect. Suppose if A is cooperating with B, then also B have 2 choices. If B defects, it's going to be free. If B is going to cooperate, it's going to get 6 months. So in this case also, B is better off to do that than that. So regardless of what A will do, B, if B is rational, that's one of the assumptions we do in game theory. If B is rational, B will always choose to defect regardless of what A will do. So if A is rational, A knows B is going to do that. So A has 2 choices, either to defect and get 8 years or cooperate with B and get 20 years. So A is better off to defect regarding in this case. So this is going to be the final outcome if A and B are rational. Even if they are friends, if they are rational, they will only look for their self-interest. That's what game theory is all about. So even though you put them in separate cells, by analyzing this, we can tell what is the outcome of this interaction is going to be. They are not talking to each other, but we can tell if A and B are rational, this is what they are going to do. Right? So that is known as Nash equilibrium. So at this equilibrium point, A or B, they don't have any incentive to deviate from that setting. That's what the definition of Nash equilibrium. But we should also know that if A and B cooperate, both of them are going to get 6 months. So that is better off. That is better in terms of, that is socially better outcome. Okay? So what is the difference between that and this is if they don't talk to each other, this is going to be the outcome. If they talk to each other, and obviously that's going to be the outcome. Right? And I will show you later in transmissions, in wireless communications, if I transmit the signal to a receiver, and that signal is going to affect other transmitters in the environment. So if I transmit some signal, I need to think about how other transmitters would transmission power in order to increase the signal to noise ratio for their receivers. That will affect my transmissions. So what I have to do is, traditionally we would just design some transmitter parameters without giving any consideration to the environment, how that's going to react to my transmissions. Now I can apply game theory principles to, and before I transmit my signal, how are the transmitters going to react, particularly if they are not communicating to each other, they don't belong to the same network, so there's a competition. So I will have to understand how are the transmitters will react to my own act, my own transmission. So I will design my transmission parameters according to that, because I cannot change my transmission parameter after I transmit the signal. So I need to think about what other transmitters would do in the environment, and then I will design my parameters accordingly. I will be doing that for radars also. Radars try to detect a target, and intelligent targets and jammers will react to that. So I need to think about how they will react, how they will interact before I transmit my signal for target detection. You understand? But then if all the transmitters belong to the same network, if they can talk to each other, then they will have the best solution. That is what a socially optimal solution. But most of the time that is not the case, then we need to understand. So that's where the game theory comes in. This is the clear so far. This is a second example of game theory. This is my town, Loughborough University. We have all the banks. Nationwide is a bank, and NatWest, and HSBC, all the banks are next to each other. Right? Probably you would have seen that if you go to a new city, if you look for money, you will walk far, and then suddenly you see one bank, and then you see all of the banks next to each other. You can explain that using game theory. So I'll give you a simple example. Suppose two banks want to build their branches in a road of length 4 miles. This is a bank known as NatWest, UK, and the HSBC probably here in India as well. So two banks, they want to decide where they want to build their branches. Okay, what is socially best solution is in this 4-mile road, assuming the households are uniformly distributed. The NatWest builds the bank 1 mile from here, and HSBC builds the bank from 1 mile from here. So no person needs to walk more than 1 mile to reach the closest bank. Okay, and what will happen if NatWest build the bank over here? Then right now they share 50% of the market. Right, customers from this side to here, they're going to go to the NatWest, and all of the customers going to go to the HSBC. So they equally share the market. But if NatWest build the branch here, HSBC would build the branch right over there. Now they have 75% of the market, because all the customers from there to there will have go to that bank, right? So if HSBC goes there, NatWest will go there, right? And then NatWest will go, the HSBC go there, and that is known as the national equilibrium. You can mathematically prove that, right? So you don't build the bank and then move. You think about these interactions, and before you build, you think about it, and then you build it, right? So this is where the game theory comes in.
If they are randomly distributed, then also randomly distributed.
Then you need, that's where the mathematics comes behind. So you need to do some mathematical optimizations where you get, you differentiate
So it is applicable uniform distributed is no problem, right?
This is an example I can explain without maths for uniformly distributed case.
Suppose it's not in, because sometimes
Then
the real life problem,
Yeah, then you also,
uniform distribution is not available.
yeah, then you can also still find the Nash equilibrium. Say for example, households are distributed not uniformly. Say more houses are here and then decreases the density like this. Still you can, using mathematical optimization, you can find the Nash equilibrium. What you do is, I don't want to go through the details, you say the x distance from here to here, you differentiate the utility with respect to x for this guy, and with respect to x for that guy, and then at the Nash equilibrium, both are satisfied. So there's no incentive for them to move each other. So you need to do a simultaneous equation of the differentiation. So you can solve that. So that's why Nash won the Nobel Prize, because you have some mathematical theory behind that. Right, my third example, before I go into my technical stuff here, there is a reason for this example. So this is a game. So I can play the game here. So the game is, I ask all of you to think a number between 1 and 100. And then I will average whatever the number you have thought. And 2/3 of the average, I will look at that. And whoever thought a number close to 2/3 will be the winner of this game. Do you understand? So all of you will think a number, and then I will ask all of you what you have thought, and then I will find the average, and I will find 2/3 of their average, and then I will say whoever thought a number close to that is the winner, right? So I'm not going to play that game here, but so most of, I asked my students before, most of the people thought a number 40 something, and some people thought 50. And I'm going to tell you, using game theory, these answers are wrong. Okay. The reason is this is about strategic thinking. So if all of you think a number 1 to 100, the maximum you will think is 100, right? So the maximum possible average is 100, right? And 2/3 of the maximum possible average is 67. Yeah. So okay, I don't want to show you the answer. 67 or 66 point whatever. So if you have thought the number 66, so you know, all of you know that the winning number cannot be greater than 67, right? So if you have thought a number between 67 and 100, that is called a dominated strategy. Okay, that is not a good, useful strategy because you know the average, the winning number cannot be more than 67. Everyone knows that, right? So then you will think about that. So you will not think of a number more than 67 because you know other people are also thinking the same thing. You know that you are intelligent and you know the people sitting next to you are intelligent and rational. So you know that no one is going to think a number more than 67. Then if I assume I'm intelligent and all of you are intelligent, then the maximum number you will think is 67, right? And the average is 67 maximum, and the 2/3 of that, 40, right? So now I know that I am intelligent, I know you are intelligent, and I know you know that I am intelligent, so no one is going to think a number more than 40 now, right? So the average of that is, maximum also is 40, and the average of that 40, and then you will keep decreasing that, and the winning number, surprisingly, is 1. Okay, that is if you are rational and if you understand the other people are rational and so on. Okay, so this is how game theory predicts outcome of any strategic interaction. Sometimes you need to do what is known as iterative elimination of dominator strategy. That's what I have done here. Okay. And then just 3 examples of convex optimization so you should understand what is convex optimization. So all of you know this, the mathematical mode optimization. This is a 2-dimensional optimization problem. Like if you have a quadratic function, this is a 2-dimensional quadratic function. If you ask me where the minimum is, that is over here. This is the contour plot of that surface, right? How you do that is you just differentiate this with respect to 2 variables, x1 and x2, and then you equate to 0, the normal mathematical optimization you will do. So this is the minimum of this problem. So this I sometimes call a cost function or loss function, and I want to minimize. Okay, in machine learning also to do loss function, and you want to minimize that, right? So that's easy. But then I will have the same problem. Now I say, okay, I want to find the minimum of that, but in that range. This range is x1, this is x-axis, x1 less than 1, x2 is less than 0. So I want the minimum of this, but in this region, below this and to the left-hand side of that. Now, the minimum is no longer that. The minimum is right over here. Because I want the minimum under that constraint. Sometimes in communications, I will try to minimize the power, total power consumption, but I have constraint. The power should be P1 or P2 should be greater than 0. Because power cannot be a negative value. Right? So if I don't worry about that and if I differentiate, I will get a negative value sometimes. So it's not allowed, right? So I have constraint. So without constraint, the minimum is here, but with constraint, the minimum is over here. That is optimization, quadratic minimization under linear constraints. This is also linear constraints where I want to find the minimum, but in this region, this is line, and this side of the line, and the minimum you can prove mathematically using some Lagrangian multiplier is going to be here. So I'm not going to take more time there on that. So this is, again, I want to find the minimum of this under this region. So where my minimum of that in that region, okay? And that region is known as convex region. So minimum is here, and the maximum is here. You can prove that mathematically. So the point I wanted to tell you is, these are known as convex optimization. So I want to optimize my loss functions, or cost function, whatever you call in your field, under some constraints, okay? So in communications also, I want to really maximize the data rate of particular transmission under some power constraints, as well as some delay constraints, because I don't want to wait infinite time for my packet to arrive, so I need to have some constraints on the maximum possible delay I can tolerate.
So it will give always a global optimization.
Right. So if the problem is convex, then you are guaranteed to have a global solution. And sometimes your mathematical optimization, the delay problem I say, is not convex. So you are not guaranteed to have global solutions. Sometimes you can approximate problems. And also sometimes people do these genetic algorithms and particle swarm, all those sort of things. But that's not possible in wireless communications because it's real-time communications. So we will approximate this problem. Normally you have high non-linearity, that's why you have local solutions. And that's why at the end of my talk I have machine learning. I'm trying to solve this using machine learning problem. Right? So because in communication I have to your data coming at a very high rate, megabits or gigabits in second. So I need to do this optimization and everything at that time. So machine learning would help that. Okay? Right. And if you are familiar with wireless communication standards, a long time ago we had 2G communication systems and then 3G. And then as we move from 2G to 3G, we had multiple antennas. Multiple antennas at the transmitter, and possibly if you see your old models, you will see 2 antennas or 4 antennas. Now you don't see that outside, it's not inside your models. So you have multiple antennas, okay? So I will be talking a little bit about that multiple antenna communication system, because that's what I have been working for many years. And then when we moved from 3G to 4G, we had multiple antennas, transmitter and the receiver, so as MIMO. And then when we move from 4G to 5G, we have massive number of antennas. So hundreds and thousands of antennas, so they can steer pencil beams to us, each of the receivers. Okay? So without going through the mathematics, I'm going to tell you why multiple antennas can steer beams to us, different mobile users. Okay? So in wireless communications, your transmitters and the receivers are fixed. So the transmitter could be fixed, but the receivers could be moving. So I have to design beams, and then I need to move the beams as the users move. So I cannot have some fixed antenna transmitting signal in one direction, right? So what I will do in signal processing, we have antennas. They are known as omnidirectional. So here I have 3 antennas. Each of these antennas transmit signal in all directions, same gain. So I have here 3 antennas. All of them are transmitting signals with same gain in all directions. However, before I feed the signal to this antenna, I can change the phase of the antenna signal that goes into these antennas. In a way, I can decide in which direction the effective pattern of this transmission is going to be. Okay? For example, by changing the phase of the signal before I transmit, I can decide that signal is radiating in that direction or that direction or that direction and so on. Okay? We're not going to go through the maths, but I'm going to give you an example about beamforming. So here I'm transmitting the same signal from 2 antennas, but there is a small distance between this antenna and that antenna compared to the receiver, right? So that distance means when this signal arrives, that signal arrives a little bit later. You see that? So if this signal arrives, and if this signal arrives a little bit later, so that if the delay between this and that is 180 degree, okay, or what will happen is this signal and that signal will destructively act. So you have one sine waveform coming like that, other sine waveform comes anti-phase because it's 180-degree delay. So that signal both is going to act destructively, so you're going to get zero gain for a receiver at that point. How about then, if I know that, before I transmit the signal from this antenna, if I shift the signal phase before I transmit by 180 degree, I'm going to have both signal arrives in the same phase. So I'm going to have this and that added together, right? So if I have a receiver here, if I know what is the delay between this and that, and from that antenna and so on, I can, before I transmit, I can control the phase so that at the receiver the effect is constructive addition. This is what we do in all wireless communication systems. So if I have a receiver there, receiver there, and receiver there, for each of these transmission I have different phase before I transmit. So when I transmit a signal to that user, that signal is not going to interfere to a signal in a different direction. That's how in 4G, 5G communication systems, etc., I can have multiple users occupying the same frequency, same time. So I increase the number of users who can access my system. That's the beauty of 4G. And 5G, you have hundreds and thousands of antennas. More the antenna means I can steer pencil beams, very narrow beams, towards the receivers. Okay, they will have their own problems. We should work on that, but I'm not going to.
Because here a delay you have to fix.
Delay. What happens is I'm going to finish my job within 1 hour. I'll just quickly tell you. What happens is when you, in all communication systems, when you, before you make any transmission, you transmit what is known as pilot signal. Okay, a signal which is known to the receiver. Okay, some particular waveform which is known to the receiver. So the receiver will look at what is the phase difference between this and that signal, and the relative phase from that antenna to that antenna. So that's known as channel gain. Okay, they know what is the channel from the transmitter to the receiver, which includes the gain and the phase. That they estimate because the transmitter first do a pilot or training signal transmission. Then the receiver feeds back that information to the transmitter. So transmitting the next time slot, adjust the phase so that all signal will arrive at the receiver at the same phase. Have I answered your question? So that in all communication we need pilot transmissions. Okay. So I don't have intention to present the maths here. You don't need to understand if you are from a different discipline. All what I want to tell you is beamformer design problem means identifying what phase I need here before I feed the signal to the antennas. Okay? That you normally use convex optimization, so you have something to minimize total transmission power, subject to every user's gets a minimum quality of service requirement in terms of what is known as signal to noise ratio. So that is you solve using these convex optimization techniques I have just shown you. And for this problem, you can, it's a convex optimization problem, you can solve it. For some problems, you need to find only local solutions, or sometimes I will be using machine learning techniques. So I will present later what machine learning techniques I'm using. Loughborough, we have looked at more interesting problems where you transmit the signal in a particular frequency occupied or licensed by some other operators. So you transmit signal without they interfering each other, known as cooperative transmissions, cooperative radios. So we used beamforming techniques, etc. So I'm not going to go through the math. Just to tell you that you will be using convex optimization to solve most of the problems. And then here is we have a multi-cell beamforming problem. So in communication you have cellular networks, so you have one communication cell here, communication cell here, and so on. If you transmit signal to your users in this cell, they will interfere to the users in the other cell. And if you don't talk to each other, if you design a beam and then if that direction is also pointing towards that user in that system, they're going to interfere each other. So we looked at here game theory, coercion game, to solve this sort of problem. So you have multi-cell beamforming. You use the game theory because we look at, even if they don't talk to each other, we will understand if I do something here, if I design beam in a particular power allocation and direction, what that cell will do for that. So I can think about how they're going to interact, react to my beam and power allocation, so that I will, before I transmit, I will consider that and decide my needs. So it's a game theory problem. We use game theory also for this problem. This is an option. Option also belongs to game theory. Okay. So this problem is probably computer science people might have studied game theory and options. So this is where you have a big micro base station. All the frequencies in that area belong to that base station. But then there are small cells, femtocells, or maybe at home level. They can use the spectrum of this macro cell for their own transmission to their users. Okay? So basically, they are using the spectrum allocated for this macro cell for their small cells for their use. Okay? So then macro cell can sell the spectrum to the small cells for the small cells to use that spectrum for small amount of time, and then they will release the spectrum, and then some other users might be using it. So in that case, this should be completely autonomous. You cannot decide at what time particular cell will be using that particular spectrum and so on. So it's an online auction. So anyone can ask the macro cell, I want to use the spectrum, and the macro cell needs to decide the price for offering that spectrum. Okay? So that is what we do is auction theory. I don't know if you are familiar with second bit auction. That's what in many countries they have done when they lease the spectrum to companies. And I think India has some issues in that. The government has asked all the operators to bid for the spectrum, and whoever win, they will get the spectrum. Okay, but all these countries use a technique known as second bid auction. Okay, how that works is, suppose if I want to sell this one to you, I ask all of you to write what you think this is worth of, the value of that, in an envelope, seal it, and you will give all your quotation to me. Right? I will open the envelope, and whoever gave me the best figure is the winner. Okay? That is also known in all auction, right? But the difference here is the price you will pay to me, the winner. Suppose if you are the winner, the price you will pay me is the price quoted by the next person, the best person. So if you quoted me 100 rupees for that, and if you quoted 95 rupees for this, and if you are the second winner, then I will give you this to you, but I will ask you to pay only 95 rupees. So winner is the one who quoted the highest price, but that winner will need to pay only the second best price. Do you understand? And that is known as second bid, second price auction system. Okay. The reason, again, you have to use Nash analysis to prove that. Mathematicians prove that if you do this sort of mechanism, where winner is the best person who gave the best score, but I will be asking you the second best score. If you do that, then mathematically it is proven all of you will give me a code which that you think that this is worth of, but you think really the value of that. You understand? Without worrying, I need to win this, so I need to give more bidding value and so on. Okay? The reason maybe you can understand that because you know you are not going to pay what you quote. You're going to pay for the second best quote, right? So you will only put what you really truly believe this is worth of. You understand? And that's what most of the countries have done when they lease their spectrum to operators. Okay? So we do the same, similar things here. And then maybe computer science people might like this. Then because we want to have some autonomous system, so anyone, any small cells can ask for spectrum and then make the payment immediately, right? So no one needs to interfere with the transaction, etc. So we combine that with auctions, with blockchain technology, so everything will be completely autonomous, so no one needs to interfere with that thing. I want to check my time. I started a bit late, right? Okay. So smart grids. So smart grids is energy transmissions of energy, and if there is an interruption, they can reroute the energy supply, etc. And so part of the smart grid is what is known as demand side management. Suppose at a home, if all of you put your appliances at the same time, then there will be peak demand, right? So the energy suppliers, they don't like that because they have to have a power generated just to cater for that peak demand, which is not efficient. So what energy providers would like is they want to somehow see the energy is used evenly at home or in the industries. So for that, but sometimes energy operators would give you price for at different time. So off-peak you will have less price and so on. Even if you do that, then if everyone puts their price at the same time during the off-peak, then that will become the peak, right? So if a number of households can communicate to each other and then if they can operate their appliances at different time, then you can minimize the power, you can evenly distribute the power consumptions, energy consumption. Which if you have a number of households, if they, through some modems, if they can communicate to each other, you can do that using some sort of centralized optimization techniques which we developed. But then the problem is all of us are selfish, right? So I don't care that when you will put your appliance, I want it now when I put my appliance to charge, right? So then we have an algorithm that uses game theory to solve that problem. Okay? So that is a potential game theory we use that is able to do the optimization in a distributed way to move the energy usage to off-peak. And radars, quickly, if you know how radars operate, you transmit a waveform, you wait for the reflection to arrive back, and then you work out what is the time delay between this signal to go and then arrive back. And then if you know the speed of the light, you know the round trip delay, so you can understand where the distance. And then you know the beamforming technique I talked to you before. Some advanced techniques are available using the same principle to understand what is the angular variable of the signal from their target, so I can locate my target. Okay? So that is the principle of radars. So what we were looking at is we have multiple radars, cluster of radars. Maybe these two radars are in Vijayawada here. Maybe that two radars are in Hyderabad. Maybe so they belong to the same unit, same military here. But we don't want them to communicate to each other because I don't want my target detection to depend on communication between these two radar systems, because the enemy can jam your communication signal and all your radar system will go down, right? So we want these radars to operate each other independently, but they all try to help to detect the target. Okay, so that is you can model as a power allocation problems and beamforming problems. But the problem is, I need to, when I allocate the transmission power for this radar, I need to understand how that is going to interact with these radars here. Okay, they need to be synchronized, maybe they need to have orthogonal waveforms, etc. So we use game theoretic techniques to solve that problem, power allocation problems and waveform design problems. So here, even though all belongs to the same unit, because they don't talk to each other, so we have to treat that as a non-cooperative game, like the business dilemma I said. Okay, because they are not able to talk to each other. So here you have optimize, knowing if I do something here, what that radar will do. I need to think about it before I optimize my transmission power. You understand? I'm not going to go through all the maths. So we solve this problem, and we have shown that Nash equilibrium is doing this and that and that. Okay. And same thing for they have to use different waveforms, orthogonal waveforms, so that they will not interfere to each other. But the problem is if I'm here in Vijayawada, I don't know what the Hyderabad radar is going to use what waveform. Okay, and vice versa. So we can use game theory techniques to understand and then optimize my waveform according to. And this is a passive radar system we developed at Loughborough University. Passive radar is we don't transmit any signals. So we use the nearby transmissions, FM station signal or digital television signals as a signal of opportunity to detect the targets. So we have an FM radio station close to the university, and also there is an airport close to our university called East Midland Airport. So we developed this passive radar system. We were able to see the flights that lands on the airport without transmitting any signals. And then in signal processing, we have a problem of target tracking. I don't know if you have heard of Kalman filters, etc. But also we have multiple target tracking. And there we have a problem when we get some measurements, we need to associate that with different tracks. So that also we can solve using some game theoretic technique. And this is obvious. This is a radar jammer interaction. So radar wants to transmit a signal to detect a target, and the target could jam that signal to avoid detection. So we need to understand if I do a particular waveform transmission, what that target would do to counteract that. So knowing that, I need to do the best I can before I transmit. So you use game theory to solve that. So most of the problem I have talked about, some of the problem are very nonlinear. So as you know, machine learning algorithms is doing a nonlinear mapping, right? So I can solve most of the problem using machine learning techniques. Particularly that is useful in wireless communications, as I said, because we have to optimize our communication parameters, waveform, or power, or beam direction, etc. at microsecond level, right? So if I cannot run a convex optimization techniques, which I can do it in the lab, but I cannot do that in a real time system. So what we could do is we can train a machine learning algorithm, which I can do that offline. I can show a lot of data, and then I can train the machine learning algorithm to tell me if I have this particular communication channel from transmitter to receiver, and if I have this communication channel from other transmitter to my receiver, and if I show all these details, the data, then the machine learning, deep learning algorithm will tell me, okay, use this power and use this beamformer coefficient, the phase adjustments, etc. For transmission. So which I can do on the fly because I don't need to train, I already trained the system. You understand? That's how it's very useful for wireless communication systems. So all of you know that I don't need to go through deep learning models, so you just put some data in, this is going to do some magic, and then it's going to tell you the output. Okay? As signal processing engineers, we love the magic inside the back propagation algorithms, etc. Okay? So that's we also use transformers, and this is the beamforming problem I have shown you, designing the beamformer coefficients, the phase that I need. So this deep learning technique is going to do that. So I'm going to tell deep learning algorithm, I'm going to show so many different channels. Channels means the transmission path, the transmitter path between the transmitter and the receivers. I will show so many different realization of the channel, and then I will show what is the best beamformer. So it learns, and then you use that when you do the real-time transmissions. So this beamformer machine learning algorithm is going to do this math. Okay, but we are just going to train it. Okay. So we developed some hardware to show that deep learning algorithm is able to do the beam steering. Yeah. And also we work on distributed learning. So you have multiple agents that train, and then they share their model parameters to the central server. So we looked at different possibilities for federated learning, and also we looked at the federated learning is very sensitive for poisoning attacks. So maybe if you have a number of malicious agents, they can inject malicious data. So my whole system will fail. So we were looking into the malicious attacks to federated learning. And this is something I was very interested in, is adversarial machine learning. So probably you might be familiar with adversarial machine learning. So this is an image of a panda. I can add a very small perturbation to this panda. So a machine learning classifier. So if I add this perturbation to this panda, and it looks to be panda still, machine learning algorithm will classify that as a different animal. So I don't add some random noise. I generate carefully. I craft some systematic way some noise and trick my machine learning algorithms. Okay, so we were looking at adversarial perturbation like this, but what we were more interested is to detect if somebody is attacking you. So if there is an adversarial attack. We have been looking at this wireless communication. It's very useful because a transmitter is communicating to the receiver, a jammer. This is a modulation detection problem or radio signal classification problem. So in wireless communication, you have different modulation techniques like BPSK, QPSK. If you don't understand, if you are from a non-wireless communication, it's not a problem. You have different signals that you transmit. The receiver needs to know what sort of signal I'm transmitting. So receiver could apply a machine learning technique to classify what sort of modulation technique I'm using. But a jammer, because all the signals are going through the wireless channel, a jammer could inject some perturbation, small perturbation, without receiver even understanding it, but the receiver will wrongly detect, classify the modulation techniques, the whole system will fail. So we were looking at that with a professor from Italy. He's well known for adversarial machine learning. This is the beauty of collaborating, because I would not have done this without the help of that other professor. Because he knows the adversarial machine learning, I know wireless communication. So this is how we learn, right? So we looked at this problem, and then what we were more interested is if there is an attack happening, to detect it. So if you detect it, then you will say, okay, I'm not going to rely on machine learning techniques to detect my signal. I will go back to my classical methods, right? Reinforcement learning, we use that also in wireless communications. Reinforcement learning, the one we were looking at is in wireless communication. If you're familiar with it, we have what's called enhanced mobile broadband. That is, you transmit big data through some resource block, some frequency and time, and then you have this ultra reliable latency communication. They are small packets, but the delay is very sensitive. When they want, you need to allocate the resources for the URLs transmission to happen, because there could be some sensing data, some real-time data you need to transmit, but they are not huge data, small data, but you need to allocate when they want the service. So then when URLC, the delay sensitive services, when they want to use the spectrum, you need to allow that to happen. So there are different frequencies they can use, different time they can use. So we use reinforcement learning to understand which is the best frequency time block for the URLs to use that. So they have to learn from the environment, right? So that's why reinforcement learning comes in. And these are recent work we have been doing. We are doing this for network slicing. So we are interested in graph neural network to solve that problem. So I even built some graph neural networks here for computer science people. So how graph neural networks works is here in wireless communications or in networks, all connected, right? So here I have, say, this is a graph. This tells you a particular transmission node, and this will be a transmission row node, and they interfere to each other. So that interference can be given by this what is known as H, and this is node, and this is how a graph looks like. And if you look at this graph, and then if I look at this point A, this is connected to B, C, and D. So that is, this A is connected to B, C, and D, right? And B itself is connected to C, and whatever that letter, and that letter, right? You can see that. So B is connected to, so 1, 2, 3, 4, this one, these connections, sorry, C. C is connected to A, B, and this and that, so 4 nodes here. And B is connected to this and that is 2 nodes, A and C. And the D is connected only to A, that is this. So this is how you map your real graph to a graph neural network. Okay? So if you are familiar with this. This is similar to your deep neural network, but here we are exploiting the structure of that relationship between the nodes. In deep neural network, you wouldn't do that. You would just put an image and you ask it to classify. But in communication or in some other applications, okay, these are related to each other. I have a communication transmitter receiver which is getting interference from that, and that communication transmitter receiver have an interference from some other communication transmitter receiver, and so on. So I can model that as a graph. And here that inside, when you combine this, you have the neural network. Okay, that's that's how the graph neural network works, and we solve that for a wireless device-to-device communication. So that means, for example, I have transmitter here T1 and the receiver R1. T1 and R1 are one unit. That's what I call here T1. And this receiver is getting the interference from T2 and T3 here. And that is what's shown as here, from here and from here. And also, for example, this receiver is getting interference from other transmitters, this one and that one. And that is what's shown here for T2. So we can model if I have multiple transmitter receiver pairs in a region, I can model the interactions using graphs. So then we use graph neural network to understand scheduling. Scheduling means I have so many devices, I need to decide which device I need to allow for transmission. And also I can decide what the transmission power should be. And also I can decide beamforming, etc. So we have done that in this paper here. I'm not going to go through the results. Now, I have done most of my presentation. If I don't have time, I will stop here because the others are what my colleagues are doing in my institute. Probably I don't need to go through that because we are good at sports, so we do machine learning, train expert system to understand how players play, and also we use that for cyber security, malicious user authentication, network security, etc. I think I'm going to conclude. I think I've done enough. Thank you for listening to my talk. As I said, we are very interested to use machine learning techniques to solve most of our wireless communications design problems. So looking forward if the opportunity arrives to work together, we're very happy to collaborate with you guys. Thank you.
Suppose when it transmits the data through signal is like when the noise contaminated with this in between, so how to tackle this issue when the noise removal comes?
Actually, we don't nowadays worry about noise so much because our traditional techniques, match filtering and known as match filtering, is able to handle the noise mitigation. Because noise is normally the thermal noise. It's distributed evenly in the whole spectrum. I can design my filter to match my transmission signal so that I can remove the noise. That's the normal thermal noise is no longer a problem. It was a big research problem 20, 30 years back. Now the problem is the sensors are decreasing, so we have interference coming from other transmitters. So if I have a transmitter receiver here, the communication interference from other transmitters interfere in my signal. That interference, if you look at the energy level of interference, much higher than the noise I have. Because we have now really good hardware with very low noise figure. So we don't worry too much about the noise. The interference is the problem, so that's what most of the communication people will be worried about.
You mean crosstalk?
Sorry?
You mean crosstalk?
Crosstalk, yes.
So in a game theory, so in the both the party you start the game, right? So rules should be know both the party, but the rules of the game. So in this case, what should the game?
Good question. So the one I have been explaining is known as non-cooperative game. So I don't cooperate with you, so nobody is going to regulate me or you. Okay, that's a different problem. And in game theory, there is a whole lot of other game theory techniques for cooperative games. So there you need to set rules. It's called known as mechanism design. So you need to set the rules in order everyone to contribute towards social the best outcome. Okay, that's a different techniques to have this so mechanism design. And some other people won Nobel Prize for that.
Yeah. For that, your problems are non-cooperative game theory is.
For non-cooperative game theory, I don't use some centralized formulation. But the solutions are supportive, as I said, they are not the best. But that's the best you can do, given that you don't cooperate.
So what should be the cooperative rules?
That is mechanism design.
So how to face the mechanism?
There are some mathematical design problems. In game theory, you have some actions. Actually, the business data, you cooperate or and then there is what is called utility. If you do this, what each of them is going to gain. So you have to design the utility according to the action in order to encourage everyone to participate. And that is a whole lot of theory behind that, known as mechanism design.
So as per the canon, one for the Traversian canon, the Traversian canon connection, so the utility function.
Yeah, utility
So
function.
that will calculate who is the highest utility function.
Yeah.
You can follow that. So that approach is.
Yeah, but utility should be for the common interest, so that's where the mechanism design comes. Right? There are some classical examples, I don't remember exactly. In the neighborhood, there is a light, you need to put a street light, and everyone needs to contribute some money to that. Okay? And so if you are selfish, you will say, okay, so someone will pay for that, so I don't worry about it. Right? And then they solve that problem with mechanism design. So that is duty functions. So that's a classical example I discussed there for the street lamp problems. I don't work much on collaborative games, except I used what is called VCR mechanism for data mining. That's long time ago, small problem.
Sir, suppose let's say one is selling at 10 price, 10 rupees, and another one is selling at 20 rupees. So according to their theory, according to the equilibrium, you can find the weight between 10 and 20, and you can find that one as a